We are Kepler's heirs, explorers of the unseen worlds beyond our sun. Guided by the spirit of Johannes Kepler, we seek to uncover new exoplanets through the lens of innovation. Our team of 4 blends science, data, and discovery into one cosmic mission. With every dataset we decode, we inch closer to finding the next Earth. We don't just detect planets, we carry forward Kepler's legacy into the future of space exploration. An exoplanet, short for extrasolar planet, is a planet that orbits a star outside our solar system. Just like Earth orbits the Sun, these planets orbit other stars in the galaxy. The first confirmed exoplanet was discovered in 1992, orbiting a pulsar named PSRB 1257+12, and later in 1995, 51 Pegasi b became the first exoplanet found orbiting a Sun-like star. Since then, thousands of exoplanets have been discovered using telescopes like Kepler, TESS, and JWST. Methods 1. Transit method. When a planet passes in front of its star, from our view, it blocks a tiny bit of the star's light. By measuring the dip in brightness, scientists can find the planet's size, orbit, and atmosphere, used by NASA's Kepler and TESS telescopes. 2. Radial velocity, Doppler. Method. A planet's gravity makes its star wobble slightly as it orbits. This wobble changes the color spectrum of the stalk's light, a Doppler shift. It helps measure the planet's mass and orbit distance. 3. Direct imaging. Powerful telescopes capture actual pictures of exoplanets by blocking the star's light. It's difficult because stars are much brighter than planets, but works for young, large, or far-orbit planets. 4. Gravitational microlensing. When one star passes in front of another, its gravity bends the light of the background star. If a planet orbits the front star, it creates a small, noticeable change, revealing the planet's presence and mass. Kepler's theory. Summary. Johannes Kepler proposed 3 laws of planetary motion, describing how planets orbit stars in elliptical paths, move faster when closer to the star, and follow a mathematical relationship between their distance and orbital period. These laws became the foundation for detecting exoplanets, as they help scientists predict how a star should move or dim when a planet orbits it, forming the basis of modern detection methods like the transit and radial velocity techniques. Design of our project. Our Project Exoplanet Detector is an AL/ML-based application designed to identify potential exoplanets from NASA's real-time CSV datasets. The system processes astronomical data, such as light intensity and transit patterns, and uses trained machine learning models to distinguish between confirmed exoplanets and false positives. By analyzing subtle brightness variations of stars, the model predicts whether a celestial object is a planet or just noise in the data. This automation reduces the need for manual observation, making exoplanet detection faster, smarter, and more efficient. In the first part of our coding demonstration, we use a CSV file provided by NASA as a reference data set. From this file, we separate the data into 2 categories: confirmed exoplanets and candidate planets. This classification forms the base of our code, allowing the AI/ML model to analyze and predict the type of planet efficiently. We use Python as our main programming language to implement this process. In the second part of our coding demonstration, we focus on confirming whether the object is an exoplanet or a candidate planet. This is done using 2 major detection methods, the radial velocity method and the transit method. The code generates a graph based on these methods, and from the Grapier's values, we calculate the radius of the planet, helping us determine whether it qualifies as an exoplanet or remains a candidate. In the third part of our coding demonstration, we developed a website for the identification of planets using AL/ML. The front end of the website is built using HTML, CSS, and JAVAScript, while Bolt and Supabase are used for web integration and data management. The AL/ML model, implemented in Python, automatically analyzes the NASA provided data file uploaded to the site. This automation significantly reduces human evaluation and makes it easier for researchers to identify and understand exoplanets efficiently without the need for manual intervention. Our project showcases how AL and ML can revolutionize the process of exoplanet detection by automating data analysis and improving accuracy. Using methods like radial velocity and transit detection, we bridge the gap between raw NASA data and meaningful planetary insights. This prototype is just the beginning. With continued development, our integrated platform aims to make the discovery and understanding of exoplanets faster, smarter, and more accessible for researchers and enthusiasts.